Hello and welcome. In this video we want to learn how we can find the vertical asymptotes of the rational functions. And also we will learn how to prove that those are vertical asymptotes. Consider these functions. All of these functions are rational functions. Rational functions are functions that are in fraction form, and in the top, in the numerator, we have a polynomial, and in the denominator also we have polynomial. All of these are examples of rational functions. For finding the vertical asymptotes of rational functions, simply set the denominator equal 0 and solve the equation, and then you can find the potential vertical asymptotes. So for finding the vertical asymptote of the first function, simply you have to set x minus 3 equals 0. And from this equation, x is 3. This vertical line, x equals 3, is a vertical line, is the vertical asymptote of this function. Let me graph here this function for you so you can understand better why this line is the vertical asymptote of that function. X equals 3. Let's suppose 3 is here. So if we suppose 3 is here, this vertical line is the vertical asymptote of that function. And graph of that function is something like this. As you can see here, x equals 3 is the vertical asymptote of that function. Also, this function has a horizontal asymptote, but this is not the topic of this video. Now look at the next function. Similar to the previous question, we have to set the denominator equals 0. So for finding the vertical asymptote, set the denominator equals 0. But this equation has no solution. So this equation has no solution. Why this equation has no solution? Why we cannot find any value for x from this equation? Because x to the power of 2 is always positive. We add 4 to that. X to the 2 is positive. 4 is positive. The sum of two positive expressions never can be equal 0. Maybe if I write this equation in the form of x to the 2 equal negative 4, you can understand this better. X to the 2 is positive. Negative 4 is negative. Never a positive expression can be equal to a negative expression. Or you can say, okay, let's find x. If you take a square root, this would be plus minus radical negative 4. But we know that radical of negative numbers is not a real number. We cannot take a square root of a negative number. So as you can see, there is no solution for this equation. But what this means about this function? This means that this function has no vertical asymptote. So we say about this function that it has no vertical asymptote. If you wonder why we discuss about vertical asymptotes and why they are important, because with the aim of vertical asymptotes, we can sketch graph of the function. They are really important when we want to sketch graph of the functions. So this function has no vertical asymptotes. But attention, don't worry if you don't know how to graph these functions. This is not the topic of this video. Just I'm graphing these functions for you here to understand them better. If I graph this function that here we have for you, you can see that it has no vertical asymptote. Its graph is something like this. As you can see, it has no vertical asymptote. Now let's move to the next question. For finding the vertical asymptote, similar to the other question, we have to set the denominator equals 0. From this if you take 4 to the other side and take a square root from that, x is equal to +2 and -2. So let me write these separately. So we have actually two potential vertical asymptote for this function, x equal 2 and x equal -2. But actually one of these is not the vertical asymptote for this function. Maybe you wonder why. Attention, this is really important. If you look at the numerator of this function, which is x2 minus 2x, you can factor x and you can write the function in this form. And if you look at the denominator, x2 minus 4 is x minus 2 times x plus 2. X minus 2 from the top with x minus 2 from the bottom can cancel each other. So we can cancel x minus 2 from the top with x minus 2 from the bottom. Then only we have this. So we can simplify this function and write it this way. Now if you look at the new denominator, you can notice that if you set this expression equal to 0, the only answer that you can find for x by setting this new denominator equal 0 is only x equals -2. And this is the real vertical asymptote of that original function. So the only asymptote for this function here is x equals -2. So we learned something new here. When you want to find the vertical asymptote of rational functions, it's always a good idea to first simplify your function, as we did here. If there is any common term between numerator and denominator, cancel them, then set the denominator equal 0. Otherwise, maybe you get answers like here that are not really vertical asymptotes. But let me tell you something about x equals 2 that we got here. What is this x equals 2 for this function? At x equal 2, if you graph this function, the graph of this function has a hole on the graph. So x equals -2 is vertical asymptote. But when an expression cancels from the numerator with the denominator, the roots of that expression, which in this case is x equals 2, make hole on the graph of the function. So x equals 2 is a hole on the graph, not a vertical asymptote. Vertical asymptotes are the numbers that make the denominator equal 0 after you simplified the function. Another way, probably you can make sure that the numbers that you got by setting the denominator equal 0 are the vertical asymptotes, is that if you plug in those numbers in the numerator must be not equal 0. Otherwise, maybe those numbers are not vertical asymptotes. For example, here, if you substitute 2 in the numerator, what happens? Then you have 2 to the 2 minus 2 times 2. This is 0. And this shows that possibly x equals 2 is not a vertical asymptote. But if you plug in -2 in the numerator, we can see that it would be -2 to the 2 minus 2 times -2. This is 8. This number doesn't make the numerator 0. And this shows that this is the vertical asymptote. So let's summarize what we learned from this question. When you want to find the vertical asymptote of rational functions, it's better to simplify the rational expression first. If it is possible to simplify it first, and then set the denominator equal 0 to find the vertical asymptotes. Let me show you the graph of this function also. The graph of this function is something like this. Attention, we have vertical asymptote x equals -2. Let's say -1, -2 is here. The vertical asymptote is here. And the graph of the function is this is the graph of this function. As you can see, at x equal to, we don't have any vertical asymptote. We have a hole on the graph of the function. But at -2, we have a vertical asymptote. Now that we have learned how to find the vertical asymptotes of the functions, let me show you how you can actually prove that. For example, x equals -2 is the vertical asymptote of this function, but x equals 2 is not the vertical asymptote. We have this function. Now we want to prove that between these two vertical lines, this one is not a vertical asymptote, but this one is vertical asymptote without looking at the graph of the function. So let's review the process of finding vertical asymptote. Simply set the denominator equal 0. We got these numbers, but we don't know which one is the vertical asymptote, which one is not. The mathematical method to prove that a line is the vertical asymptote is that you have to find limit of the function. So we have to find limit of x to the 2 minus 2x over x to the 2 minus 4 as x approaches 2, and another limit when x approaches -2. If this limit approaches infinity, this shows that this line is the vertical asymptote. But if it doesn't approach to infinity, this line is not the vertical asymptote. For finding this limit, first we try direct substitution. But if we plug in 2 in numerator, it is 0, denominator is 0. So direct substitution doesn't work, so we think to other methods. We factor numerator and also the denominator. X minus 2 cancels. What remains is limit of x over x plus 2 as x approaches 2, and the limit is 2 over 4 or 1/2. As you can see, the limit of the function when x approaches 2 is not infinity. So this means that this is not a vertical asymptote. Actually, as we discussed before, we know x at x equal 2, for this function, the graph of this function, we have a hole. So by doing this limit and by finding the limit, we can say this is not a vertical asymptote. Now let's see what is the limit of function when x approaches -2. So we want to find limit of x to the 2 minus 2x over x to the 2 minus 4 as x approaches -2. Maybe you wonder why I made the limit like this, why I made it limit from the right and limit from the left. I will explain it in a moment. The reason is that you cannot find this limit as a two-sided limit right away. You have to make it a limit from the left and a limit from the right. Similar to all limits, first we try substitution, direct substitution, to see if we can find the limit or not. If you plug in -2 in the numerator, this would be -2 to the 2 which is 4. And then we have negative 2 here times negative 2. It is also 4. 4 plus 4 is 8. So the numerator is 8. Also here we would have 8. Because again, we substitute negative 2 in the numerator, we get same number. But the denominator is important. When we plug in negative 2 in the denominator, negative 2 to the 2 is 4. 4 minus 4 is 0. Also in the limit from the right also we get 0. But the difference is in the zeros. When x approaches negative 2 from the left, x is a number close to negative 2. Attention. Let's say, suppose negative 1 is here, negative 2 here, negative 3. When x approaches negative 2 from the left, x is somewhere here. If you raise a number here to the power of 2, because here we have x to the 2, that number would be positive 4, but a little, just a bit greater than 4. Attention, x is something like negative 2.1. You can imagine for yourself that x is this. If we raise it to the 2, this would be 4.41 or 4 point something. It's clear. It is greater than 4. And if we subtract 4 from that, from this subtraction, we get a number close to 0 but greater than 0. But for the other limit, the opposite of this happens. Because x is close to negative 2 from the right side. It is somewhere here. And when you raise it to the 2, it would be close to 4 but less than 4. So the result of subtraction would be negative. Now from all of this, what we have? The first limit, the limit of the function would be infinity. The other limit would be negative infinity. And because at negative 2, the limit of the function is infinity, this means that at negative 2, we have vertical asymptote for the function. The function approaches at vertical lines. If you look at the graph of the function, you can see that it is true that we have vertical asymptote at negative 2. Negative 2 is here, and as you can see, we have vertical asymptote. Let's review the result of the limits. When x approaches negative 2 from the left, the function approaches infinity, which is confirmed here by the graph. Look at here. When we approach negative 2 from the left, the graph of the function, look at this graph, it goes to positive infinity. But when x approaches negative 2 from the right, if you pay attention to the graph of the function, it goes to negative infinity. So, for finding the vertical asymptotes of a function, of a rational function, simply set the denominator is equal 0. And by setting the denominator equal 0, you are finding the potential vertical asymptotes. To make sure that it is a real vertical asymptote, you have to find infinite limits like I did here. If the limit was infinity, it is vertical asymptote. But if the limit is not infinity, it is not a vertical asymptote. Let me show you one more example. Consider this function. Y equals to x over x to the 3 minus x. You can find vertical asymptote simply by setting the denominator equal to 0. But it would be better if you pull out x from the bottom like this first, cancel x from the top with x from the bottom, and simplify your function like this. Attention, the expression that we cancelled from the top with the bottom is x. This means what? This means that at x equals 0, attention, we cancel this x from the bottom and the top. When you cancel something from the top of a fraction with the bottom of the fraction, by setting that expression equals 0, you can find a hole on the graph of the function. So if we graph this function at x equals 0, there is a hole on the graph of the function. And attention, it is not vertical asymptote, it is just a hole on the graph of the function. So I highly recommend you, when you want to find the vertical asymptote, simplify the function before setting the denominator equal 0. In this way, you prevent to find numbers that are not really vertical asymptotes. Now, in this simplified version of the function, I am going to set x2 minus 1 equals 0, and then from that x equals plus 1 and x equals minus 1. These are the vertical asymptotes. These are vertical asymptotes of my function. And again, that x, if we set it equal to 0, is not a vertical asymptote, but it is a hole on the graph of the function. If we graph this function, you don't need to know the graphs, so don't worry for that. But I'm graphing to get an understanding about the function and the vertical asymptote. Vertical asymptotes are 1 and negative 1. We have one vertical asymptote here at negative 1 and one vertical asymptote here at 1. And the graph of that function is something like this. But at 0 we have a hole. Attention, here we have a hole on the graph of the function. This is the graph of that function. Again, attention, here I didn't prove that these vertical lines x equal 1 and x equal negative 1 are vertical asymptote. If you want to prove that these are vertical asymptotes, they are vertical asymptote. We can see it in the graph. But if you want to prove it with the limits, with the infinite limits, you have to find limits of the function when x approaches 1 and when x approaches negative 1, like I did in the other question here. But I'm not going to do it for this question. I hope by watching this video you have learned how to find the vertical asymptotes of the functions.